Hello, everyone. Can everyone hear me? Just before I start. Yeah, cool. Awesome. We'll get started with this week's tutorial. So this week's tutorial is essentially a continuation of what we did 2 weeks ago when we covered max flow, and then towards the end we'll also cover some introductory DP as well. So we'll cover some dynamic programming problems as well. So let's kind of recap what we did a few weeks ago. So we essentially covered the max flow problem of given a flow network. What you wanted to do is you wanted to compute the maximum flow from S to T. And in lectures, you would have seen that, in fact, the value of the maximum flow is actually equal to the value of the minimum cut as well. So there's this nice duality between the maximum value of any flow from S to T and the minimum cut. And the minimum cut is the smallest cut that separates S and T. So for the first half of the tutorial today, we're going to basically use this duality to come up with algorithms to solve the problems that we want. And then in the second half, we will cover dynamic programming. Uh, and there are a couple of algorithms out there that allow us to compute maximum flow. So there is the Ford-Fulkerson algorithm with running time O of E times the value of the flow. Then we also have Edmonds-Karp. So Edmonds-Karp gives uh, I believe it gives something like v times e squared. And these are the only two algorithms that we're allowed to use in this course. But of course, other algorithms exist. So you can have Dinnick's algorithm, which runs in v squared e. You can also have other algorithms like Borland, which runs in v e time. And there are more and more algorithms out there for you to compute maximum flow. But for the sake of this course, we're only allowed to use these two algorithms here. Cool. Oops. Uh, so let's have a look at our first problem. So the first problem is you are given a collection of jobs. So you're given a set of jobs. And for the sake of notation, we would index them from 1 to n. And you have two processes available to run them on. So imagine you have a bunch of jobs, and what you have are two processes. What you would like to do is to assign jobs on processes to minimize the cost. So the way that the cost function works is you can run job I on the first processor at a cost of AI, or you can run the job on the second processor at a cost of BI. But not just this, but you also have this network cost. So if you have two jobs that are assigned on different processes, then they incur a network cost of Cij. And for simplicity, we'll assume that this network cost is symmetric. So if you place a job on processor 1 and a different job on processor 2, then swapping their arrangement will give you the same cost. And so the goal is to assign some subset of jobs onto processor one, and then the remaining jobs onto processor two, so that this cost here is minimized. Okay. And the hint here is to model this problem as a min-cut problem. So somehow what we would like is the value of a cut is equal to this. So this should correspond to the value of a cut. So are there any ideas on how we might construct the flow network? So any thoughts? So if I want to construct my flow network, I want to define my vertices and my edges, and I want to define the capacities on the edges. So what would my vertices be? I have a vertex for each job and a vertex for each processor. Okay, we can try that. So one suggestion is um, vertex for each job and a vertex for each processor. Okay, and then what do you do from here? So if you have a vertex for each job and a vertex for each processor, then how would you define your edges? And another suggestion is your vertices is your jobs. So we'll get to that in a minute. But let's just try to like entertain this idea first. Maybe like okay, so what kind of problem are we trying to solve here then? If we have a vertex for each job and a vertex for each processor. So let's imagine we have a set of jobs and then we have a set of processors. Well, actually, we have two processors. So actually, we have uh, two vertices here. Okay. So and then what do you do here? So we'll define a source and a sink, and then we'll have like edges to each of my jobs, and then we'll have edges to my sink. But it seems like it's a bit difficult to define what these edges are. Uh, an edge between each job and processor. Okay, sure. So we'll have a something like this, and it's something like if this is processor one and processor two, you'll have uh something like this. Okay, this seems reasonable. The only issue here I have is that how do you model the network cost? So this is easy to kind of separate out your jobs. So your cut essentially represents kind of like your partition into your two processes. But how do you, so the question here is how to model network cost. And it seems like this is not powerful enough for us to properly do this, right? Like if I just consider a cut, or if I consider just the maximum flow, the value of any flow, this doesn't really take into account the the cost between two jobs where they rely on different processes. So perhaps this is not the right way to think about the problem. So another suggestion was to look at vertices as jobs. Okay. Um, if we have vertices as jobs, so uh, the other suggestion was vertices. How would I define my edges between my between the jobs? So you can imagine I have like a bunch of jobs here. I'll have a source and a sink. So I want to define three types of edges. I want to define edges from the source to some vertex, vertices to vertices, and a job to the source. Maximum flow, Fs flow, C's capacity. Yeah. But okay. So what would the flow represent? Okay. Or what would the capacity here represent? No edges between jobs. So do you mean just having something like this, and then you'll have we'll do orange, and then you'll have like, is that your flow? So if you have no edges between jobs, you get something like this. Um. Okay. So how do we model? Okay. So how do we model the flow network? So what is like the idea of the flow network? So like, okay. So what does it mean to have an edge between two jobs? Add another edge between source and jobs. Well, we already have an edge from the source to every job, so you can't really add another edge. You can just increase the capacity if you want. Yeah. So I think we have kind of like the right ideas. So what you want is the following. So the source to so what you can think about is the source is kind of like one processor, and the sink is another processor. So the fact that we have two processors means that one side is the source side and one side is the sink side. So then the way that we're going to build it is beforehand we don't know which jobs are going to land in which processor. So let's just make an edge from the source to every vertex with capacity uh, AI. Oh, I guess in this case we'll call it BI, and you'll see why in a second. Um, you have an edge from a job I to T with capacity AI, and then you have an edge from I to J with capacity Bij, and it's exactly the same reason as what Sarah gave. So two jobs are assigned to different processes if they have an edge between them. Well, if they have it, essentially, if the edge in the min cut, well, if you consider any cut, then that basically separates the jobs into one processor and another processor, and the set of all jobs that lie in that cut will contribute towards that network cost. So that's a way to think about the network cost here. So let's kind of break this down into three parts. So this is essentially just saying we assign to processor 1. Here we assign to processor 2. So in this case, we've separated out we've basically partitioned the set of vertices into two parts. And then here, this is going to be the set of all edges that cross my cut. So set of all edges that cross the cut. Cool. So let's actually prove this. So I claim that basically this is the construction of my flow network. So I just have three types of edges. Source to every job to the sink, and for every pair of jobs, I construct an edge. I guess this is a bidirectional edge as well. I construct an edge I to j and j to I with capacity C of ij, and then I claim that this is if I run the maximum flow algorithm, then I get the correct partition. So let's see why. Okay, to see why, let's consider any ST cut. So let XY be any ST cut in the flow network. What I'm going to do is I'm going to show that in fact the value of this cut is exactly equal to this this value here. So if I consider any ST cut, there are three types of edges that contribute towards my cut. So there are three types of edges that contribute to the cut. Do we know which ones? So which three types of edges are going to contribute towards my cut? So maybe it might help to think about the types of edges that actually contribute to the cut are exactly those of the form x to y. So it's any vertex from x to any vertex in y. But they come in three types of edges. Can we... No idea? Okay, so what I have is the first one is s to I for every I in y, right? So if I imagine that x is the source side of my cut, this is going to contain s, and y is going to be the set of all vertices on the sink side. So all of the edges from s to vertices in y are going to contribute towards my cut. So if I look at this, these red edges are going to contribute towards my cut, but only the ones that are in y. So the ones that are in x are not edges of the form x to y. Okay, so we have s to I for every I in y. Can we describe the other two? Yeah, so edges from s to an edge on the right hand side of the cut. What are the other two types of edges? So we had one from the source to everything on the right hand side. What's another one? So maybe one that includes a sink. Specifically, what edges I to T? Yeah. Where does I belong then? So we say I to T, but I needs to be in a specific set. So I can't be in any set. And I to J, yeah. For what values of I and what values of J? Cool. Uh, so yeah, so for all I in X, well, yeah, X minus S, I guess. And then I to J for each I in X and J in Y. Right. So these are all of the edges of the form. So I guess here it's you don't include T because there's no edge from S to T. But cool. So okay, so first of all, does this make sense? That we can separate out the um so we can separate out the set of edges this way. And so we can look at each one of them separately. If we're happy with this, we can move on. Uh, so yeah, I can draw a sample graph. So imagine I have my jobs. So I have job 1, job 2, job 3, job 4. Then what I have is I have my jobs plus my two, my source and my sink. What I'm going to do is I'm going to have three types of edges. So I will actually color code them. So it's a black edge. This is a purple edge, and then this is an orange edge. So the black edges are going to be of the form S to everything, and then I'm going to have my I to T. So I'm going to have this kind of edges, and then I'm going to have ones in between. This my black edges are going to have capacity B of I. Purple ones are going to have capacity A of I, and then the ones in between are going to have capacity C of I, J. Yeah, cool. Now, okay, so we've basically separated out the types of edges that contribute to the cut. So let's have a look and see what the value of the cut would be. So let's have a look. So the value of the cut is going to be the black edges plus the purple plus uh the orange ones. So for the black edges, well, this is going to be the set of all edges. Oh, so the sum of all of the capacities from S to elements in Y. So this is going to be the sum of all jobs in Y, C of S to I, plus, well, the purple ones are the ones from I to T. So that's going to be the set of all jobs in X, the capacity from I to T, plus the orange ones, which is going to be the set of all jobs that are in different processes. So I in X, I in Y, C of I to J. Okay. So what we're going to do is we're going to look at these three cuts separately. So remember that a set of black edges have capacity B of I. So in fact, this is just going to be the sum of all elements in Y of B of I. Thus, the capacity of the purple edges are going to be A of I. So this is just going to be I in X of A of I plus the sum. So this C of I to J just has capacity C of I J. So you're going to get the sum from I to X, I to Y, C of I J. Right. And so you can imagine that like the set of elements in X corresponds to the set of elements in S. So if you imagine X is equal to S, then what we have is a set of all jobs not in S plus the set of jobs in S plus this other sum here. Cool. And this is exactly the cost function that we want. So if you look at an example of a cut here, so let's say let's change color just so that we know. Let's say that I cut it this way. So what's going to happen is I have on one side maybe all of these elements, and then on the other side we have all of these elements. So if you look at the set of all of the edges across this cut, what I have is this edge here, this edge here going this way, this edge here going this way. Oops. This edge, or maybe I'll use a different color. This is a bit, okay. So I'm gonna draw it with blue. So what's gonna happen is this edge is going to contribute towards my cut. This edge is going to contribute towards my cut. This edge is also going to contribute towards my cut. This edge is going to contribute towards my cut. And then all of the edges from the source on this side to any vertex on this side. So for example, here, and here as well. And yeah. Right. So you can see that in one cut we have so I guess these edges, this one, and this one, these okay, I'll do it this way. I'll use black. So these are the set of edges in the first part. Right? So it's the set of all edges from S to anything that's not in the source side, plus the set of uh, jobs in the source side to T. So that's exactly this edge here. And then the last part is the set of all jobs in different processes. That's exactly equal to the remaining jobs. So that's going to be this one, and this one. And you can see that only one direction is going to be counted because the other direction is going to go from Y to X instead. So when you do that bidirectional thing, only one of the edges will be counted, so you're not double counting things. Does that make sense? And so you can see that a cut corresponds to this cost here. So this is the value of the cut. And so, of course, if you compute the maximum flow, that corresponds to the minimum cut, right? And because we showed that the value of the cut is exactly equal to the thing that we want, it just suffices to compute the maximum flow, and you can do this in O of VE squared time. Cool. The number of edges is, well, bounded by O of n squared. So this would be at most n times n squared squared, which is going to be n to the 5. Cool. So here the tricky part is to realize that actually we can model this as a flow network. Once you see that you can model this as a flow network, then everything else here is pretty straightforward. So yeah, so whenever you have these kinds of min-cut problems, there's usually only 3 types of edges that you need to care about in your cut. So it's the set of all edges from the source to the set of vertices that are not in the source side, the set of all vertices in your source side to the source, so to the sink, and then the set of all edges from the source to the sink. N times n squared equals nqy. So here, then we are looking at v times e squared. E here is bounded by, well, you can think of the graph here as a complete graph, because for every pair of jobs, we have a bidirectional edge. So actually, the number of edges that we have in this flow network is 2n plus something like n squared, or on the order of n squared. Okay, so this one is not actually a bipartite graph. Usually, the types of flow network problems that you'll get are bipartite, but sometimes for harder applications, you'll see that it's not necessarily a case of bipartite graphs, because we're not necessarily actually constructing the bipartite graph. Here, what we would like to do is to partition the set of vertices, or the nodes in your float network, into 2 parts. And by partitioning this into 2 parts, they have to mean something. So in this case, the partition means you place one set of nodes on processor 1 and the other set of nodes on processor 2. Yeah, so usually with flow network problems, the hardest part is to think about how to construct your actual flow network. Because once you know the construction of your flow network, uh, the rest is just a case of running the algorithm, and you can assume that the algorithm is correct. Cool. Are there any questions with this problem? Yeah. So to recap, what we have is we've turned the problem into a problem of computing a min cut. So what we showed is that this was actually the value of the cut, and then what we wanted to show was well, so once we showed that it was the value of the cut, then we just used the fact that the value of the maximum flow corresponds to the value of the min cut, and so you can obtain the partition that you want from your max flow. Cool. And if you want to actually return the schedule to compute the minimum cut, what you do is in your final final graph, you just run a BFS, right? So you run a BFS to get set of vertices that are reachable from S, and that's one side of your partition, and then the remaining vertices form the other part of your cut. Cool. We'll do more examples. So here we're going to basically do a very similar thing. We're going to model the problem as a min-cut problem, and then we're just going to run our max flow. So here you're given a set of n courses. Each course has an associated benefit, which can be positive or negative. So you can think of the negative benefit as, well, you don't prefer it. So there's a negative benefit to actually taking the course. In other words, some courses may be poorly run that incurs negative benefit. Different courses have different prerequisites. In order to choose a course, you need to also choose all of its prerequisite courses. A course can have many prerequisites, and a course may be a prerequisite to many courses. What you want to do is to come up with a set of courses that are feasible, and we say that a set of courses is feasible if the prereq of every course in X also belongs in X. So in other words, if I have a set of courses that I would like to take, I must also include all of its prerequisite courses. So even if there are courses I don't want to take, but those are prereqs to the course I want to take, I have to take those. So imagine that this is like the set of courses I want to take, but then in order to take this course, I need to take this course and this course. In order to take this course, I need to take this course. And so therefore I must include all of these courses as well. And what you want to do is you want to return the benefit, the profit. So you want to return a set of feasible subset of courses such that the total profit is maximized. Okay, so how would you do this? Any thoughts on how you would go about approaching this problem? Why did we make BI the capacity for... So you didn't really need to. The reason why we chose BI here was more to do with the fact that we wanted X to be the set of courses that we choose, or not courses, the jobs on processor one. So in other words, there was really no need to make BI the capacity from S to I. The idea was just we wanted the set of, so we wanted processor one to be the source side and the and processor two to be the sync side, but you can easily just swap them if you wanted to, and just swapping those also gives you the correct answer as well. So there really wasn't a need to do that, but I think if we wanted to make processor one the source side and processor two the sync side, then in order to get this kind of cost, we needed to swap uh, the capacities. And you can see this in the analysis, right? So when you do the analysis here, S to I corresponds to the source side. So you have B of I, but you're summing up B of I over all of the jobs on the sync side. But there was really no need to make. So you could make the source side processor 2 and then the sync side processor 1 if you wanted to as well. So there was a suggestion, find out the relations of all courses, connect them with edge BI. Okay, S to all V with no prereq, V with no out. Okay, so why do you put S to all be with no prereq. Is there a need to do that? Is it necessary to do that? So okay, so how do you enforce? So if you wanted to take a course and you knew that another course was a prereq, how would you enforce your algorithm to also choose that particular course as well? So if I had a course that I wanted to take, it's included in the set of courses I want to take. How do you also ensure that this other course has to be connected to this course? So what kind of capacity could I enforce here? So to do this, we incur an infinite capacity. So if it turns out that your algorithm chose this course, then it has to also include this course here. So what we can do is we can basically enforce the prereq condition to be true by just constructing an edge with capacity infinity here. Yeah. So basically, the algorithm will just follow the set of paths to other courses. Cool. So let's actually start constructing the flow network. So as usual, the kind of separation I want is on the courses. So what I would like to do is to set my set of vertices to be the set of courses. So vertices is going to be the set of courses plus my S and T. Now for each course, so now I'm going to construct my edges. There are three types of edges I want to construct, right? So S to uh, I to T, and I to J. So let's think about this a little bit. Um, okay, so uh what kind of edges should I make here? This one's a little bit harder. It's not as straightforward. Can we have negative benefits? Yeah. So there is so in the problem here, we allow benefit to be negative as well. So it's not just positive benefit. Otherwise, the problem is trivial, right? Because if every benefit is positive, you just take everything if you want to maximize your profit. So in order to make the problem interesting, you also need negative benefit. Otherwise, you just take everything. So let's go back to this. So this one's a little bit trickier. So I'm actually going to write out um, the flow network. So this is you're going to construct an edge from S to I if the benefit is positive. And we're going to construct this edge with capacity BI. Right. And the intuition for this is because we don't really ever want to choose a course with negative benefit. So it doesn't make sense to have um, it doesn't make sense to start with an S to uh, some course with negative benefit. So we have an edge from S to I whenever we have positive benefit, because we don't really ever want to take a course with negative benefit. And then here, from I to T, this is if the benefit here is negative. and we're going to have capacity minus BI. So when BI is negative, then this capacity will be positive. So it doesn't break any kind of condition here. And then from I to j, this is just a prereq condition. So um, you just construct an edge if prereq ji is true. With infinite capacity. What if the university is so bad that there's only negative benefit? Well, that's also trivial. You basically just take nothing. You just don't do any course. The university is so bad. Why would anyone want to pay for the university? So you just don't do any course. And the algorithm will also find it as well. Or, if you wanted to do it this way, then you just turn the problem into positive benefit, you take everything, but then you just take the complement of everything, which is to take nothing. Yeah. So this one's a little bit trickier. So I'm just going to give you the actual flow network. You're not really expected to, like realistically, a problem like this is not going to come up um, in your labs or in the exam. I think this is a bit too hard for the course, but it's still an interesting problem. So what we're going to do is actually we're going to prove that the profit of x for any cut is going to correspond to this. So let's see how we can prove this. So again, as usual, we're going to let xy be the cut, be any st cut. And again, we're just going to kind of look at your the set of edges that contribute towards the value of the cut. So here we really only have two types of edges. So the two types of edges that we get are S to I, or I in Y, and I to T, or I in X. Right? You're not going to have any other types of uh, edges in my cut. Okay, so then what we can see here is if I look at the value of my cut, that's just going to be equal to the sum of all of the edges in Y of the capacity from S to I plus the set of all edges in X, which is with capacity I to T. Okay, and what does that look like? Well, the set of edges from S to I is going to be have capacity B of I, where B of I is positive. So let's write that. So that's going to be I in Y of BI plus the set of all edges, or the set of all courses in X with negative BI. Right, so that's just by definition of my capacities. Okay, now what can we see here? Well, X and Y partition the set of all courses, not including my S and T. So this is really going to be, what can I do here? The set of all elements in C minus X of BI plus the set of all courses in X of, okay, I'm going to pull the minus out, and that's just going to turn into b of I. Okay. And, okay, so what can we do here? So I'm just going to write it out again. So here we have um, I in C minus X, B of I minus the set of courses in uh, X of B of I. Okay, so where do we go from here? Um, so remember, the set of courses here we have is all positive. So what I'm going to do is I'm just going to basically pull this out. So I'm going to write it as I in C as long as B of I is positive, greater than 0, of BI minus uh, the set of courses in, I believe we get X, where B of I is positive, minus this other set here. Here, remember that the set of courses are all negative. What am I going to get here? So I'm going to distribute out the minus. So I'm going to get the set of courses where it's positive, minus, well, this is just going to be the set of courses in X, where the benefit is positive, plus where the benefit is negative, right? But this part here is exactly equal to the set of all courses in uh, in X. So this corresponds to exactly all of the courses in X, because we look at all of the courses that are positive here and all of the courses that are negative here. And so a course can either have positive benefit or negative benefit. We'll assume that no course has zero benefit because they don't really contribute to the analysis here. So we'll assume, without loss of generality, that everything is either positive or negative. So what we can see here is that this is actually just a profit of X. And here, what can we say about this part here? Does this portion of my sum uh, correspond to anything about my cut? So remember, I had a cut. I had the cut XY. Here we have this. We have the set of all courses where the benefit is positive. Does this actually um, have anything to do with our cut? I guess that's my question. So is this sum here affected by the value of my of any cut, or is this something that's like completely independent of my cut? Do we have any ideas? No. Yeah. So notice how the things that we're summing here is the set of courses. So this is the set of courses, And the only things that we're summing up are the set of all causes where it's positive. But this has nothing to do with the value of my cut. So this is actually just a constant. All right, and so this is independent of any course that we have, of any cut that we have. I don't get the negative stuff. Okay, so let's go through one at a time. So remember that if you consider any arbitrary cut, any arbitrary ST cut, what we have is the set of edges that actually contribute towards my cut come from either the edges of the form S to I for all I in my source side, and anything on my anything on my sink side, and then anything on my source side to T. So these two are the only edges that are in my cut. So we'll look at these two separately. So what we have is so basically the cost of the value of the cut is just the sum of the edges from S to I plus this set of edges from I to T. So this is just by definition what the value of my cut is. Then you can then notice that well, the only edges that contribute towards my cut are exactly the ones where here B of I has to be positive, and here my benefit has to be negative, right? So I could have other vertices in my x and y, but the only ones that actually contribute towards my cut are exactly those where B of I is positive here and B of I is negative, right? Because that's just by definition how we define my edge S to I. So you can kind of just like break this down into two parts then. So by definition of my C of S to I, my capacity, this is just B of I, where B of I again is positive. So I'll probably just write this. And here my B of I is negative. So this is just by plugging in my capacity. So remember that C of S to I is B of I, which is greater than 0, and then C of I to T is minus B of I, where it's negative. So hopefully from here to here, it's not too hard. It's just plugging in the value of your capacities. And then from here to here, all we're really doing is just we're pulling out the minus sign. So the minus sign goes at the front. And so now we can start to think about the definition of a cut. So by definition of a cut, really the x to y here means x and c minus x. So everything on my source side plus everything that's not on my source side. And so we can separate out my I can redefine y as the set of courses that are not in x. And so I define it basically this way, where again we're only looking at courses that are positive, and here we're looking at courses that are negative. Does this make sense so far? So how we go from here to here to here? Okay, so from here, so I've kind of just like I've just rewritten it here. So now we're getting into kind of the more tricky part of the analysis. So here, in the first part of my sum, remember that everything here is still in terms of the benefit being positive, and here, everything here is in terms of the benefit being negative. So from here, what we're going to do is we're going to break it down into two parts. So it's going to be the set of all courses with positive benefit minus the set of all courses in X with positive benefit. So by definition, this is what this big sum here is, right? So I look at all of the courses with positive benefit, and then for you to have a course in C minus X, I need it so that I'm subtracting away all of the courses that are not in. I'm subtracting away the courses that are in X, and that gives you exactly the first part of the sum. And then here, I just kind of left it by itself. And then from here, I've just kind of combined these two parts, right? So I can just pull out the factor of the minus factor here. And now I have everything in X with positive benefit and everything in X with negative benefit. But this is exactly just equal to the sum of all of my BIs. Right, so this is just the sum of all of the BIs in X, and that's just equal to the profit of X. So now the question here is like, what is this other sum doing here? And it turns out that this is actually just a constant in terms of my cut. So I can just pre-compute this if I wanted to. And this doesn't change according to the cut. So no matter which cut I take on the same flow network, this is still going to be the same. So this is just going to be a constant in terms of my cut. And then this is just the profit of X. So in fact, what I have is the value of my cut is equal to a constant minus the profit of X. So the profit of the set of courses on the source side. So now what I have is if I minimize this cut, so minimize cut actually corresponds to maximum profit, right? Because if I minimize the cut, the only thing I need to do is, well, this is a constant, so this doesn't change no matter, like, this doesn't change no matter what the cut is. So the only thing I can do is to affect the profit. And in order to minimize the value of my cut, I need to maximize the profit. So in fact, what I can show is actually the min cut corresponds to the max profit. And I know how to compute min cut. Min cut is just the max flow. And so now I have an algorithm that computes the maximum flow, which computes the minimum cut, which corresponds to my maximum profit. And so now you can run any flow algorithm. So you can run something like Edmonds cut. And Edmonds cut will compute this in O over V E squared. And here, again, E can be as large as n squared. So E is O of n squared. So now you have an O of n to the 5 algorithm. Cool. Does this problem here make sense? If it makes sense, then we will skip the last one. I'll leave it to you to think about this one. Uh, Essentially, it's the same idea. You just you can kind of just copy and paste the same kind of argument from this problem, but I'll leave it to you to think about. We will take a short 5-minute break, and I will leave you with this break time question. So the question is, can you pack 53 bricks of dimension 1 by 1 by 4 into a 6 by 6 by 6 box? And then for the remaining 10 or so minutes, we will do dynamic programming. So as a question, may you repeat why min cut equals profit? Okay, sure. So remember that what we said was the value of the cut was equal to this constant minus the profit of x. Alright? So, and if we minimize this cut, so if we minimize cut, that means we want to minimize this constant, maybe not x, we'll call it a. We want to minimize this constant minus this profit. But because a is a constant in terms of any cut, a is something that we can't really control. So the only way to affect uh, this value is profit. And if you just kind of recall from basic algebra, if you minimize one side, which is equal to a minus uh, z, then in order to get the minimum value for this for the left side, what you want to do is you want to maximize this value here. So in other words, what you're doing is you are computing the minimum cut, and once you compute the minimum cut, that corresponds to your maximum profit. So profit is equal to constant minus my cut. And so if I'm minimizing the cut, then I'm maximizing my profit. So it might help to think about it like this. And once we have this, then we can see that if I minimized my cut, that means on the other side, I maximize my profit. It's okay. So it's not necessarily the case of smaller max flow being greater the profit. It's more the case of the smaller my cut is, the greater my profit. So then what I want to do is I want to compute the smallest cut, which corresponds to the maximum flow. So you can broadly think of it then as if I maximize my flow, then I maximize my profit. So the flow actually corresponds to my profit. But here we just want to think of it in terms of min cuts, because the problem itself naturally gives you the correspondence to cuts. So it's more the case of the smaller my cut is, the larger my profit, and vice versa. And so if I want to maximize my profit, I have to minimize my cut, and then the minimum cut is equal to my maximum flow. No worries. Yeah, so I'll leave it with you to think about this problem for another 2 minutes, and then we'll resume with some dynamic programming problems. So yeah, there was a question about so don't understand why c minus x can be divided into. Okay. So x itself is not the set of courses that are larger than zero, where the benefit is larger than zero. In fact, X is just an arbitrary set of courses. So that there are some courses that are positive with positive benefit, and some courses with negative benefit. So, um, okay, so remember that okay, so let's do it this way. So remember that we can broadly define the following. Okay, let's do it, yeah. So remember that if I look at A minus B, if I look at any element in A minus B, this is just the same as a set of all elements in A, and not in B. Um, so if I look at the set of courses, so let's not do that. So if I look at any course in C minus X where B of I is greater than zero, then this is just the same as saying the set of courses where B of I is in zero, where B of I is greater than zero, and X is not in X of B of I is greater than zero. So in other words, we're looking at the set of courses in. So we're looking at the set of all courses with positive benefit. So if we take the sum, so then if we take the sum over all of the elements in C minus X, where I have positive benefit, then what I'm doing is I'm looking at all of the courses with positive benefit first. And then I'm excluding all of the I'm excluding all of the courses that are in X with positive benefit, because the only courses that are in the set are all the courses with positive benefit, but then the courses I'm excluding are the set of courses that are in X. So then this is minus the set of courses in X with positive benefit. Yeah. So X itself is not necessarily the set of courses that are have negative benefit. It's just that we look at the when we're defining the cut, or when we're defining edges in the cut, we only look at the edges with negative benefit. But actually, X could contain courses that have positive benefit as well. So X itself is not necessarily defined by the set of courses that have negative benefit or positive benefit. It's more a case of um, uh, X itself is just a set of courses. So there's no like meaning in terms of this benefit as well. Would the finals be as hard? I would not assume so. I think I think these flow problems are probably as hard as it gets, and I don't expect any problem relating max flow min cut for algorithm design specifically to pop up in the exam. You might be asked like, oh, what is the min cut of this really simple flow network? But you're not expected to use min cuts to solve algorithm problems. But these are just fun problems that are sort of extensions of the kinds of concepts that you've seen in class. Cool. All right. So for this one, I will just leave you with the answer. The answer is no, and I'll leave it to you to think about why. All right. So now we're moving on to dynamic programming. Um, so in actual calculation, the set x should be empty. So if you're looking at x, so if you're looking at x in x that are where the benefit is positive, this is actually not necessarily empty. Because remember that X itself is just a set of courses. So there's no meaning behind b of I greater than 0 or b of I being less than 0. It's only the case where we look at the value of the edge from x to y. So we define um so remember that x and y are just arbitrary is an arbitrary partition of my vertex set. And what I have is I only consider the edges. So I only consider the edges um, on the source side where the benefit is positive, and on the sink side where the benefit is negative. But x and y itself could contain courses that have positive or negative benefit. So here I look at specifically the kinds of I look at I look at specifically the courses that have positive or negative benefit, but X and Y itself might have both positive and negative. So here in the cut, but X and Y itself could contain uh, positive and negative benefits. Cool. All right. So now we'll get started with dynamic programming. So typically with dynamic programming, you have essentially um, you basically have a structure. So whenever you think about dynamic programming, here are the kind of things you want to think about. So you want to define a subproblem definition. And the subproblem definition should basically be, one of the subproblems you want to define is essentially what the final solution is. So you have a subproblem definition, which is kind of a breakdown of the problem into a simpler version of the problem. And we'll talk about what that actually means as we do the questions. Then, using a subproblem definition, you want to define a recurrence. And so this is how you relate different subproblems together. And typically, what you'd want to do is you want to memorize subproblem solutions. And then once you define your recurrence, then you want to think about the base case or base cases in the case of where you could have multiple base cases and your final solution. You want to think about order of your computation. And finally, proof of correctness and time complexity. So this is kind of the scaffold that you typically have with a dynamic programming solution. So you start off with a definition for your subproblem. Then using that subproblem definition, you define a recurrence. And then you have base cases, final solution, order of computation, and then you prove your correctness and your time complexity. So let's have a look at this problem as a start. So a subset is spaced if it does not contain any pair of consecutive integers. Let A be an array of n positive integers. Our task is to compute the maximum sum of values that come from a spaced subset of indices. So in other words, if I look at this array, 2, 4, 3, 5, then we have the following spaced subsets. So 1, 2, 3, 4, 1, 3, 1, 4, 2, 4, and then we just return the maximum among all of these spaced index sets. So remember that the spaceness, like the property of spaced, is on the index set and not on the actual values. So for example, I could have 2 and 3. So 2 and 3 themselves are consecutive, but the indices are not consecutive. So we only care about the consecutiveness of the indices rather than the actual value itself. Okay, so the first part is to come up with a greedy solution. So let's look at this greedy solution and we'll show that this does not actually work in general. So choose the index corresponding to the maximum element, remove its neighbors, and then we'll repeat this until no more indices are left to choose. So in other words, we always want to choose the maximum value that we can, and then remove the invalid choices. So here we have, okay, so what we want to do is want to provide an array to show that this doesn't always work. So I'll leave it to you to actually do it yourself. There are many solutions, so I'll leave it to you as an exercise. So let's actually start working with the actual dynamic programming solution. So we need to come up with a definition for our subproblem. So what is a suitable subproblem definition? So let's think about an example. So let's say that I have these. Basically, you can think of it as I have this set where this is maybe x1, x2, x3, x4, x5, and x6. What I can think about is, well, let's suppose I have just an arbitrary space set, maybe something like this. How would I construct this recursively? So let's start by just thinking about like this last element here. So in this last element in my space subset, um, if I choose x6, then I know that I can't choose x5, right? And so the question is, now I basically want to look at, okay, so assuming I choose x6, I basically look at the space subset of this set here. And then I choose the maximum over all of the possible space subsets here. So what could my subproblem definition be in this case? So let space of I denote what? So if I define space of I in terms of this parameter I, what would that parameter I be? So remember, if I look at this example here and I chose x6, then it boils down to the same problem of computing the space subset of this set here. So what I can do is I can just define my space subset subproblem to be the maximum space subset chosen from the set of indices from the set 1 to I, right? And so from here, I can define my recurrence, and the recurrence here is based on whether I choose spaced I or I don't choose. I choose index I or I don't choose index I. So let's look at two cases. So if I look at the first case where I choose index I, what would the solution to this be? So here, my space of I would be uh, whatever A of I plus what? So it might help to think about the problem a bit recursively. So I've chosen this index. So if I want to append this index to something else, then it has to be whatever the maximum space subset is among all of the possible indices that I could choose from. And it's exactly equal to this set here. So what would my recurrence look like? So it would be, well, whatever the maximum space subset is from the set of indices that I can choose from 1 to I minus 2, right? So this here represents maximum space subset chosen from set 1 to I minus 2. Yeah. So Francis has said it correctly. Yeah, space I minus 2. Cool. So then, okay, so this is the first case, right? I choose index I, then I take a of I plus space of I minus 2. But in the second case, I if I don't choose, so if I don't choose index I, then the problem just reduces down to, well, if I don't choose my last element, then I just choose the elements from 1 to I minus 1. Oops. Right? So if I just discard this element here, then the problem just boils down to computing the maximum space subset from 1 to I minus 1. So that would just be space of I minus 1. Cool. And so the solution is just to look at both of these cases and just take the maximum. So the recurrence would just be, well, I don't really know which one is better, but my algorithm will just compare these two values and just take whatever is the maximum. So it would just be the maximum over space I minus 1 and a of I plus space I minus 2. Does this make sense? So any possible space subset would either take the last element, and if it takes the last element, then it can only choose from the index set 1 to I minus 2, or it will not choose the ith index, and so it would then choose from the set 1 to I minus 1. And it would just take whatever is the maximum out of those two cases. Cool. Yeah, and then we'll finish off with some base case. So for this problem, I'll probably just write it out. So the base case occurs when I equals to 1 and I equals to 2. And space of 1 is always just going to be a of 1. Here we're assuming you have positive integers, otherwise you take the maximum between 0 and a of 1. And space of 2 is just the maximum between a of 1 and a of 2. Right? So if I can only choose from the first two indices, yep, I can zoom out. So if I can only choose from the first two indices, then I just take whatever is the maximum. So the only possible space subset is either A of 1 or A of 2. Cool. And the correctness is quite easy to show. If you look at any space subset of the index set from 1 to I, it will either contain the ith element or it won't contain the ith element. In the case where it contains the ith element, you know that it can't choose the I minus 1th element. So whatever the maximum space subset is among the index set from 1 to I minus 2, it would just append that A of I. In the case where I doesn't belong in my set, then it's just going to be some subset from 1 to I minus 1. And then you can prove this by induction that this works. So, does anyone have any questions with this problem? Yeah. So the final thing is to do is, well, base case, final solution. Final solution is just space of n, and then the time complexity. Well, you have n subproblems. You have a subproblem for each index, and then for each subproblem, you're just computing, assuming you've computed everything in advance. So assuming you've computed space of I minus 1 and space of I minus 2, all you're doing is you're doing a bunch of checks. So everything here is constant time to solve. So it's O of 1 per subproblem. So you have a running time that's O of n. Cool. Okay. So that was the first problem. So hopefully it's not too bad. So the trick with dynamic programming is you want to think about your subproblem definition. Um, and you want to think about like specifically how you would design the subproblem definition so that it kind of matches the time complexity uh, of the problem. Yeah. So what does the subproblem do here? So the subproblem itself is kind of like trying to figure out how to utilize your inductive hypothesis. So the subproblem here is really just saying, I'm going to solve this intermediary problem. So I'm going to simplify the problem a little bit by not necessarily solving the entire problem, but solving smaller versions of the problem itself so that when I get to the final solution, I can just use the fact that I already know the solutions from everything previously to then extract what the final solution here is. So the subproblem itself is kind of like your the smaller versions of the problem that you're trying to solve. So notice how the problem that you wanted to solve was to find the maximum space subset. Here, the subproblem is to find the maximum space subset, but from a more restricted set of indices. So it's kind of like a more general problem, so that when you get to the subproblem that you want, which is your final solution, you know that you've already computed everything in advance. Do we declare it first instead of using it directly in the... So what you do is, like when you're actually coding it up, you're usually using a bottom-up approach. So maybe I'll actually write out like a kind of... It's not really code, but it's kind of like an idea for how to think about it. So there are typically two ways to think about the dynamic programming. So the way that you think about the code is you define the dynamic programming table. In this case, the dynamic programming table is just the space of I. So here you're defining a single array of size n. And initially, you can initialize everything to uh, initialize space of 1 to be 1, a of 1, and space of 2 to be the maps between a1 and a2. And then from here, you basically update your dynamic programming table using the recurrence. So then the recurrence goes, well, I can update space of I by looking at max of space of I minus 1 and a of I plus space of I minus 2, right? And the trick here is that we've already computed this and we've already computed this as we're going up the uh, so as we're computing this in increasing order of I, we know that we've already computed space of I minus 1 and we've already computed space of I minus 2. We store that in memory, which is what you define initially before you do everything. And then from there, all you need to do is just to pick out uh, the values that you actually want. So here you want a space of I minus 1 and space of I minus 2. When you're actually proving it by induction, what you do is you just assume that the uh, previous subproblems are already solved correctly. So what you do is you just assume that they're solved correctly. And then using the fact that they're solved correctly, you want to justify why this recurrence here is true. So assuming that space of I minus 1 is the sum of all of the values in the optimal uh, in the optimal space subset from 1 to I minus 1, and space of I minus 2 is the optimal sum from 1 to I minus 2, how do you combine them together in a way where you get the correct solution? Does that make sense? If so, then we will continue. So here, what we have is so the subproblem is to find so I mean the subproblem itself and the recurrence go hand in hand. So if you have the correct subproblem, you'll be able to find the recurrence very easily. So if you define the subproblem in this way, that's good. But then you need to use that subproblem to find the recurrence that you want. And so then you have this nice recursion between of your subproblems. I think it will be uh, you'll be able to see it a lot more once you do more practice with it. So I will leave it to you to think about how it works as you do your lab problems. Cool. Um, you are traveling along a river by canoe. Along the way, you come across N trading posts. So imagine you have these trading posts. Uh, the cost to rent a canoe from post I to post J. So say that you start here and you end here. The cost to rent a canoe from I to J is given by f of ij. You start canoeing from trading post 1, and you want to end at trading post n, and you want to design an O of n squared algorithm for this. Okay, so how would you do this? So again, you need to come up with a suitable subproblem. So how would you define a problem? How would you define the subproblem for this problem here? So what would your subproblem definition be? So let rent. So I'll give you a hint. You have one parameter. So now you need to think about what that parameter would be. So let's say you have some way of going from 1 to n. So it might help to think about, like, say you have a way from going from 1 to n. Maybe you go from here to here, here to here, and then finally here to here. How do we think about this problem recursively? Have one trading way, or you always start at trading post 1. But what you don't know is you don't know where you're ending, right? So you could go from 1 to n, but that could be very expensive. So it might be the case that you go from 1 to some other uh another trading post, and then go from that trading post to n. I is the cheapest to n. Yep. So minimum cost from what 1 to I. Correct. Yep. So your subproblem definition would be, or rent of I would be the minimum cost to get from uh, from trading post 1 to I. Okay, so let's think about this with a picture. So I'm going to redraw the picture. And let's suppose I have a way of going from 1, this is I, 1 to j, and then j to I. Okay, so this is, for example, a way of going from 1 to I. How would I construct a recurrence based on this picture? How would I construct a recurrence for this problem? Yes, assume you find the cheapest uh, from 1 to some index. So how would you find a recurrence to find uh, the cheapest way to go from 1 to I? So let's think about this picture a little bit. So we have a way from going from 1 to j, and then we have a way of going from j to I. So you can imagine that you have like a sequence of canoes that you've rented. So maybe you have a sequence of canoes that you've rented from 1 to j. So it's a sequence of canoes. And then you go from j directly to I. Right? So this is one example of a trip from 1 to I. So you can think about the journey as, well, I want to find the cheapest way from well, okay, so I can break up the journey into two parts. I find a sequence of canoe trips from 1 to some index j, and then I take a canoe from j straight to I. And the cost to go from j to I is f of ji. What is the cheapest way from 1 to j? So, ooh, what is the cost of the cheapest trip from 1 to j? Yeah, rent j plus fji. That is very good. So if I look at this sequence where I go from 1 to some index j and then I go directly from j to I, well, the cost of going from j to I is just f of ji, and the cost of the cheapest trip from 1 to j is just rent of j. It's just the subproblem itself. Well, okay, so we want to go from 1 to I. That's our subproblem that we want to solve. But what we can do is we can go from 1 to j using a sequence of canoes. So here we're going from 1 to j first, and then we're going to go from j straight to I. So we're going to rent a canoe to go from j to I. So what we want to do is want to find the cheapest trip via canoe renting from 1 to j, and then we add on the fee to go from j to I. Does that make sense? So we want to find the cheapest trip from 1 to j, and that itself will solve the subproblem to go from 1 to I, right? Because we just add on the extra fee where we go directly from j to I. So we can think of the trip. So we can think of the trip as a sequence of canoes from 1 to j plus the canoe from j to I. Cool. And so rent of I is equal to, I'm going to leave some space out here because we're going to figure out what exactly this part is. It's going to be rent of j plus f of j I. Okay, I've left out some space because this is not exactly correct. What goes here? So what we want to do is want to figure out what exactly goes here. So remember that this was just a trip where we wanted to go from J directly to I, but we don't know what J is. How do we figure out what this J is? So J was just some like intermediary trip. So we went from 1 to I via some canoe from J, but we don't know what this J is. So what do we do here? So remember the subproblem itself was we want to find the min cost. So somehow we need to find we want this kind of min definition here. So what is like the missing part? We want the J that gives the min cost. Exactly. So we don't know what that J is. We don't know the J that minimizes this. But what we can do is we can just, let the algorithm compute the min. So we want the min of this constraint where J is just that intermediary canoe. So the intermediary canoe goes from 1 to J, 1 to I. So here, what we can think about is if I have the sequence of trading posts, my J could be 1, so I can go directly from 1 to I. So that's the J equal to 1. Or I can go J equal to 2, and I can go from here. Sorry, I can go from here to here, followed by this point to this point. Or I can go from or if I have J equal to 3, then I can find a sequence of canoes from 1 to 3, and then fly to 3, or fly to from 4, or fly from up to I minus 1. So I basically brute force all of the possible uh, values I can have for J, and then I just return the one that gives you the minimum, right? And so that gives you the recurrence. Okay, so once we have the recurrence, we need the base case. So here the base case would be rent of 1. So what is the cheapest trip to go from 1 to 1? Like, what is the minimum cost to go from trading post 1 to trading post 1? 0. Yep, cool. So rent of 1 is just 0. What is my final solution? So what subproblem stores my final solution? Yeah, so 0 because you don't need to travel. You just stay at that particular trading post. And then what would my final solution be? So what is the subproblem that I want to return? Or subproblems I want to return? So remember that the subproblem itself was the min cost to go from 1 to I, where I goes from 1 to n. And the problem that we want to solve is the smallest cost of traveling from trading post 1 to trading post n. Rent 1, which is the same as rent. Well, rent 1 is not the same as rent n, because rent 1 is the min cost to travel from 1 to 1, whereas rent n is the min cost to travel from 1 to n. So they're not quite the same. But yeah, the final solution is stored at rent n, because this gives you the minimum cost to go from trading post 1 to trading post n. Okay. And then we solve this in increasing order of I. So of I and time complexity. So how do we justify the time complexity here? So what we have is, well, a number of subproblems. So how many subproblems do we have? N? Yeah, cool. So there are n subproblems. And how long does it take approximately to solve each subproblem? So time. So if I look at the recurrence, I'm looping through all of the possible values for j between 1 and I. So how much work do I need to do uh, for my subproblem to solve my subproblem? Oh, then correct. Yeah. So the time taken to solve each subproblem is approximately on the order of n. So the final time complexity is, well, we have n subproblems. Each takes approximately O of n to solve. So the final time complexity is just the number of subproblems multiplied by the time to solve each subproblem, which gives you O of n squared. Right. So it's number of subproblems multiplied by time for each subproblem, and that gives you about O of n squared time. Cool. There is one more question, which is a bit more interesting. But I will leave it actually to you as an exercise. I think it's very similar to the first problem that we did. So, if you understand how to do the first problem, which is the space subset one, then and you know how to do the second problem, then I think you should be able to solve the third problem on your own. Are there any questions with any of the problems that we did today? So my general advice with dynamic programming problems is to actually draw out some examples. Uh, in very simple examples, it's good to kind of like have a visualization of what's going on. Usually with like partition style problems, what you want to do is you want to look at the last part of your partition, and then you look at all of the possible values. So for example, here, we can think of this as a partition of like, I want to go from 1 to j, and then I want to go from j to I. So I'm partitioning into two parts. What you can think about when you're doing the subproblem or when you're doing the recurrence is you basically want to find the point at which the last part of your partition happens, and then the remaining part of your subproblem is actually just solved recursively. So that's usually a way to visualize what's actually happening with dynamic programming. With this problem here, it's kind of the same, but this time you want to figure out if you want to choose the last element or not. So if you want to choose the last element, then the problem boils down to just ignoring the previous element and then choosing everything else. If you don't choose it, then it boils down to choosing the remaining indices. So it's always good to have a visualization of exactly what your recurrence is doing, and how you would come across the recurrence itself. But otherwise, I think it's just a matter of doing a lot of practice, and making sure that you're comfortable with defining subproblems and how you would come across the recurrence itself. Are there any questions that anyone has? Yep. So consider where the last trip J to I is. Yep. So you don't exactly know where it is. So it could be the case that it's actually cheaper to go from I minus one to I. But say arbitrarily you just choose a particular place for J where the last where the last rent happens. So you can broadly think about the partition as a collection of canoes that you rent. There's always going to be some last canoe that you're renting. So you want to think about like, okay, if I rent the last canoe, I start from J, some index J, and I have to land at uh, trading post I. So I look at the the amount it, the cost that it takes to go from J straight to I, and then from there, the problem then boils down to, okay, I want to go from 1 to J somehow. So if I know I want to go from J to I, then I need to choose a way to go from 1 to J such that you minimize that cost as well. So then the whole cost of that trip is just the min cost to go from 1 to J plus the fee. And so you minimize over all of the possible ways you can go to I, or you can go straight to I. And that's like the idea uh with that problem. Does that make sense? No worries. Are there any other questions from any of the four problems that we did today? If not, then we can probably end it here for today. Um, Hopefully we can release problem sets pretty soon. Um, I'm usually the one who writes them, so they should hopefully be out pretty soon. It's just been a very busy time period for a lot of us, but yeah, hopefully we can get them out. If not now, then in time for your exam, and then you can use that as practice. And feel free to ask on the forum if you are stuck on any of the problem set questions as well. Cool. Other than that, I don't think there's any other news from me. So I will see you guys next week where we cover more interesting dynamic programming problems. Okay.